So this is video 3, week 11. We are now covering new material with pointers, and we're going to start with pointer arithmetic. Okay, so we just covered how you can use subscript and offset notation on both pointers and arrays. You can use either or, whichever you prefer, because they're basically the same thing. They both point to an address in memory for a variable. Okay, so here we have some pointer arithmetic. Pointers can be used in assignment expressions, arithmetic expressions, and comparison expressions. Kind of something we can't do with references, right? C++ allows pointer arithmetic. So not all languages give you pointer arithmetic. I think we were talking about Java last week with pointers that you can't do pointer arithmetic, okay? And you'll see what I mean by arithmetic. Don't think I know it's a more fancy word than it sounds, but it also works with raw arrays, okay? And we'll take a look at a couple examples here. So plus plus and minus minus, that's kind of what I'm talking about here when I say arithmetic, all right? So here, the plus plus is going to increment this pointer to point to the next array element, okay? So the pointer's pointing to address whatever hex value for my number variable. When I do is, let's say it's in an array, okay, and I have a number array, an int array, and I have 0, 1, 2, 3, 4, 5, whatever in the array. And my int pointer is going to be pointing to the very first memory for the pointer is 1000, which is going to be pointing to the first element, so 0. If I do plus plus, it's going to increment by whatever size my machine allocates for an int. Okay, so it could be 4 bytes, it could be 8 bytes, it could be varying depending on your machine. So now after I do int pointer plus plus, it's going to be pointing to 1008 or 1004, which is going to be the second element in my array. Okay, decrement or decrement, however you say that, a pointer, it's going to decrement the pointer to point to the previous array element, okay? So you can do minus minus and it will go 1008, 1004, 1000. So we can increment by size of data type, okay? So if you have a double, an int, a vector, which is a very large data type, it'll increment by the size within the array, okay? So just handy to know that we can do pointer arithmetic, okay? Now taking a look at another example, just using plus and minus now, what we can do here is we can actually increment the pointer by any number of size of element that our pointer is pointing to. So here I've got n times size of type, all right? So the size of data type for my machine, personally, I know this because I tested it. I've done the size of variable is 8. But I know commonly and typically, for most people, it's 4. Okay, so 4 bytes for an int. Okay, so here I'm doing int underscore pointer plus equals n. Now n, we can see, was n times size of type. So what this basically is going to be saying, I write it out in int pointer equals int pointer plus n. So I don't have to just increment it by one element doing plus plus. I can actually increment it by 3 elements or 4 elements, right? So here I could say my size of int on my machine, size of type int, is 8. And if I want to increment by 2 items, then 2 times 8 is 16. So now this is going to say whatever the address of my int pointer was, which is 1000, plus equals 16, it's going to say 1016. And that's going to be where my int pointer is now pointing. So it's the same thing as the last slide, except it doesn't limit us to just doing plus plus. It allows us to increment by however many we want. Decrement is the same. You can decrement by whatever number, and you can use the shorthand minus equals, or you can just do int pointer equals int pointer minus n number of elements you want to decrement by. We can also compare pointers using some Boolean logic, so using the equals equals or the not equals sign operators, and we can determine if 2 pointers are pointing to the same location or not. Okay, this doesn't compare the data where they point. It just compares the address of where they're pointing to. Okay, so here we have string 1, string 2. Okay, string 1 is Frank, string 2 is Frank. Okay, they're both Frank. They're both the same text. Okay, now I've made 3 pointers. I've assigned pointer 1 to the address of string 1. Okay, I've assigned pointer 2 to the address of string 2, and I've assigned pointer 3 to the address of string 1 again. If I compare P1 and P2, okay, they're both Frank, but one is pointing to S1 and one is pointing to S2. If I do equals equals, it's going to be false. Use my my pen here. So let's say this has an address of 1000. Oops. Okay. And this has an address of 2000. That's the address in memory where these live. Okay. So S1 is 1000, S2 is 2000. P1 is set to the address using the address operator of S1. So this is going to be 1000. P2 is set to the address of S2. If we look up at S2, the address is 2000. So this is going to be 2000. And then P3 is set to S1 again, which is going to be 1000. So when we compare here, we're basically pointing up to the 1000, and here we're pointing to the 2000. So yeah, 1000 does not equal 2000. Right? So that's going to be false. Now the next one's comparing P1 and P3. Well, P1 is 1000, P3 is 1000, right? So that's going to be 1000 equals 1000, which is true. And I see something in the chat here. Someone asked if we have equals 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 in C++. No, that's JavaScript. Or at least not that I'm aware of that I've used. All right. All right, did that make sense? Good. Okay, that's making some sense. We're setting in a couple of things here. That's good. All right, so the data that they're pointing to is not considered when checking for equality, right? So just because both strings are Frank, that doesn't matter. Okay, because we're not doing Frank equals Frank. We're doing the address of S1 and the address of S2 right here. Okay, good. All right, moving on. We can also compare the data that the pointers point to. So just like the example I showed you where we compared the addresses, we can also compare the data that they point to by using the dereference operator, right? The dereference operator gets us the value at the address. So the value at S1's address is Frank. The value at S2's address is Frank. Okay, so again, I'll annotate here. The address here is 1000. The address here is 2000. Okay, but because I'm using the dereference operator here, okay, it's going to go to S1, okay, address 1000, but then it's going to use that dereference operator and get the value of Frank, okay? So it's going to store Frank, oops, here. Okay, now here I've also dereferenced P2, which is set to the address of S2. Well, the address of S2 is 2000, but I've used the dereference operator, so I'm going to be getting the value at the address of 2000. Well, the value at the address of 2000 is Frank. So that means that the dereferenced version of P2 is Frank. You might be able to see where this is going, but I'll do it one more time for P3. P3 is also dereferenced, uses the asterisk. It points to the address of S1, which is 1000, but because it's dereferenced, we get the value, and the value of S1 is Frank. We have Frank here. Okay, so now basically we can see these are all the same. If we compare P1 and P2, that's like comparing this one and this one, which is going to be true. And if we compare P1 and P3, that's like comparing this one and this one, which is Frank and Frank, which is also going to be true. And look, that's what we get. We get true and true. Okay, so hopefully that makes sense. Using the dereference operator, you can get the data that the pointer points to and compare it. So we can use the equals equals. Just have to dereference it first. Cool. Passing pointers to functions. All right. This is a whole other section, and this can get confusing, but hang with me because once you get it, it's not actually that confusing. It can be confusing at first, but it's not actually that confusing. Okay. There are several ways to qualify pointers using const. Okay. Now, this sounds confusing. We have pointers to constants, we have constant pointers, and we have constant pointers to constants. All right. It's a mouthful, even for me. That sounds like a lot. We also don't have to use const at all when passing something to a function. Just remember, if you want it to be read-only and you don't want to change the data or allow the user to update the data, then maybe it's best practice to use const. All right, the const qualifier gives us more fine-grained control of what we want to allow to be changed. So we can have pointers to constants. So we could have an int that's set to 100, and we can point to that int, and the int itself is a constant. Okay, the pointer is pointing to that int, and the int 100 never changes. We can also have constant pointers, which is a pointer that points to an address in memory. So that address in memory might be 1000. That means that pointer will never change from pointing to 1000. And then we can also have constant pointers to constants, which is both of those last two that I just said mixed. So you have a pointer that's always going to be pointing to the same address of 1000, for example, and at that address you have an int that's set to the value of 100, and it can never change from the value of 100. So your pointer will always point to that variable, and that variable will always be that value. All right, so that's a pointer, that's a constant pointer pointing to a constant. I know it sounds crazy. We'll try to get some visualization. These will be very useful when we're passing pointers to functions, okay? So here we're going to start with pointers to constants, okay? So using the const keyword, and depending where you put it, changes a lot, okay? So you have to make sure you know where you're putting the const keyword when you write it out. The data pointed to by the pointers is constant here and cannot be changed. The pointer itself can change and point somewhere else if we want, but the data that the pointer is pointing to will never change. So here I've got int high score 100, int low score 65, okay? I create a pointer here and I assign or initialize it to high score. So the address of high score. So I'm going to annotate again. Oh, my screen just went black. Oh, I'm going to annotate. So here we have our value of 100, and maybe our address is 1000. Okay, that's our hex value in memory. Here we have 65, and maybe our address is 2000. Okay, so here I've got score pointer, and I set it to the address character here, which is the ampersand symbol, and we're setting it to the address of high score. So here's our high score variable, and the address is 1000. So this is set to 1000. Okay, that's what the pointer is set to. And it's going to point to an int. We know that. These are both ints, so that's good. And we made it a const int that it's pointing to. So it can only point to a const int, which means if we try to update, here's a dereferenced pointer. So we're trying to update the value to 86. We're going to get an error because here you're trying to change the value to 86. The value is 100, okay? Here, what we're doing, this may look confusing, we're setting the pointer and we're changing what the pointer is pointing to. That's allowed, but changing the value of what that pointer is pointing to is not allowed. I know that sounds confusing. So let me repeat this. We have score pointer. it points to an int that's a const, okay? So that int that it points to will never be able to change. So here, we're pointing it to high score. And once we pointed it to high score, which is the address of 1000, it has a value of 100, okay? This is my wall between them. This is the address. I can do A for address. This is the value, V for value. Okay, so once we have a score pointer here and it's set to 100, this can never change. Okay, 100 will never be able to change. But we can still change what the we can change and be set to the address of 2000, which will have a value of 65. And you're saying like, hold on, 100 just changed to 65. No, it didn't. We changed what the pointer was pointing to, and this 65 can never be set to anything else, right? That's a no-no. We cannot update the value. Here, we also cannot update the value. Okay, so you can change what the pointer is pointing to, 1000 to 2000, right? The address in memory. But once you have your pointer pointing to something, we can't update the value at that address in memory. Okay, so that's what a pointer to a constant is. We're free to assign another address to the pointer and point somewhere else. But if we attempt to change the value of the pointer, what it points to, then we'll get a compiler error. Okay, now we have constant pointers. So this one's a little bit different. In the case of constant pointers, it's the pointer itself that's constant. So the data pointed to by the pointer can be changed. The value at that address can be changed via the pointer. However, the pointer itself cannot be changed and can't point to anything else. Okay, so we'll annotate again. All right. The data pointed to by the pointer can be changed. The pointer itself cannot be changed. So here we have, again, int high score 1000. I'm going to give it an address of 1000. And here we've got our int low score set to 65. And its address in memory, the hex value, is 2000. Okay. Now here I've got my pointer, score pointer, and it's to itself is a constant. See how the const is connected to the asterisk key symbol there when you're declaring a pointer? So it points to an int, but the pointer itself, the address that it points to, is constant, can't change. So once I initialize it to the address of high score, so using the address operator, I look at high score here. The address is 1000. So this is now equal to 1000, okay? My score pointer is equal to the value, take that back, the address of 1000, okay? That's what my pointer is going to be printing out if I print out what my pointer's pointing to in the address. Now, if I try to use the dereference operator on my pointer and set the value of that address to now be assigned to 86 instead of 100, okay, so right now it's 1000 and it's set to the value of 100. If I try to change this to 86, that's okay. That's totally fine. I'm allowed to change the value. But if I try to change the address, okay, to a new address, so here, low score, if I look at low score and the address is 2000, this is not okay. This is okay. But we cannot change the address of what the pointer points to, all right? It has to stay 1000 always, but we can change anything of the value, all right? Notice we're still using the const qualifier. However, we use it before the asterisk in the pointer declaration, so we're declaring score pointer as a const pointer to the integer. All right, hopefully that makes sense. Clear that. And now we have our finale. Right, so the data pointed to by the pointer is constant and cannot be changed, and the pointer itself cannot change and point somewhere else. So in this case, we have to use the const qualifier twice, okay? We use it to declare that what we're pointing to and the value of it will never change. And we also use it to declare that the address of what we're storing in our score pointer variable, right, that address that we're pointing to also will never change. So we have const int, const score pointer, all right? So again, I'll draw out my addresses in memory here. So I've got 1000 and 2000. I've got high score and low score, same as before. And I'm setting my score pointer equal to the address of 1000. Okay. Now, the value is set to, well, let's take a look. We use our address operator. So our address of high score is 1000. And high score has a value of 100. So we have the address of 1000 and the value of 100. Now, if I try to use the dereference operator and update the value at this address, okay, so the address is 1000, and I try to update the value to 86, right, like this, no can do. Sorry, you're not allowed to change what the pointer is pointing to. Whoops, right here. Just scratch that out. Also, if I try to change where the pointer is pointing by updating the address here, remember, low score, this is the address of 2000. If I try to change this to 2000, sorry, can't do that. It's a constant. You cannot change. Once it's set to 100, it's set. That's what it's pointing to. That's the value of what it's pointing to. You can't change it. You get a compiler error. Okay, so hopefully that makes sense. So now we know those are the three ways we can pass a pointer to a function. You can also pass a pointer without any constants, and then everything can change. And then when we pass it to a function, we use pass by reference with a pointer parameter, okay? We can use pointers and the dereference operator to achieve pass by reference into our function. And the function parameter itself, so what it's expecting as an argument, is a pointer. The actual parameter can be a pointer or the address of a variable, okay? So let's take a look at an example about how to pass a pointer into a function. So here we have a function called double data. So it's going to take in some data and it's going to double it, and it's a void. So it doesn't return anything, and you don't need to return anything because remember, pointers change the values and the addresses in memory. So you don't need to return it back because it's already been updated. The original variable is changed. So don't get the star confused here, like the little asterisk with the multiplication sign, okay? Here, it's a multiplication sign. So I'm doing times equals 2, which basically means this pointer times this pointer times 2, right? Don't get that confused with the dereference operator over here, which is just going to be getting the value of what's at this address. Okay, so let's do a little bit of annotating again and take a look at this. So here we have a void, so we're not returning anything, called double data, and it expects a pointer that points to getting a dereference. All right, so we have a dereferenced pointer, and that's that key character with the asterisk there. And then in the actual function itself, how it works is it gets or receives that argument with the dereferenced pointer, and then it takes the dereferenced pointer and times it value by 2, or you can kind of look at it like this. This is the long form of the short version here. Int pointer equals int pointer times 2. All right, so if, for example, we have our address of 1000, all right, and at that address is the value of 100, and we pass in our int pointer, okay, so int pointer points to 1000, but we're using the dereference variable, so the dereference variable gets this value. What's going to happen is we're going to get this 100 equals 100 times 2. So you're going to get 200. Oops. That you're going to get 200 is what that int pointer will be set to. And so that we do not have to return in a return statement because that will automatically be set up here to 200. This is done. And now we still have the same address pointing to it, but now it's 200. All right. That's how passing a pointer to a function works. Now, we can also pass by reference with a pointer, okay, by calling the function. So here, instead of using the dereference operator, we're using the reference or the address symbol. So I'm in my main function here. I've got an int with a value of 10 that's initialized to, and I see out to the user 10. All right, now I call my double data function, which I just had on the past screen. We did it with an example of 100. If you passed in 10, it does 10 equals 10 times 2. 10 times 2 is 20. And we passed in our value. Okay, that's how you pass in the actual value. So this is how the function's written. This is the prototype that you'd put at the top of your program so it knows, so the compiler can help you and give you hints. And then when you actually call it, you pass in the variable with the address operator in front of it, okay? And then it passes that in and returns, does the logic, and then when we see out, we don't have to use the return a return statement or anything. We just have the value of 20, okay? So let's go to CodeLight and take a look at my week 10 passing pointers to functions 1 example and kind of get our hands dirty with this. Week 10 passing pointers to functions. Here we go. All right. So here we go. We've got the example from the PowerPoint. I'll close this. Is it big enough for you guys? Can you see it on the screen? Maybe I'll scroll in a little bit. Okay, so you can see it, perfect. So here we're using namespace std, just like normal, and this is our function double data. Now I'm not using a function prototype because my function is actually coming in front of my main function, but best practice would be to use a function prototype like I taught you 2 weeks ago. Now, here we have our local variable called int pointer, okay? It's declared right here. And basically, right. And here we have a compound assignment that basically outputs to it int pointer equals int pointer times 2. And I just said the same thing. Don't confuse this asterisk for the multiply symbol. Here it's multiplying. Here it's dereferencing. Okay. Now, in my main function, okay, this is all the code is. I've created my value, and then I have initialized a pointer to null pointer. So this is setting to address 0. So there's no garbage data in there. It's actually initialized, but it's set to address 0. Now I print out the value of value, which will be 10, right? That's just how an int works. We know how that works. It prints out 10. Then I call my double data function, which is up here on line 7, and I pass in the address of value, okay? I don't pass in value itself. I don't pass in 10. Let's say 10 lives at the address of 1000. I'm passing in 1000. And then what's going to happen is it's going to go up to my function here on line 7 and pass in that address of 1000 or whatever my address might be. And then it takes the address and dereferences it. So it breaks it down and it gets the value at that address and times it by 2. And look, I don't have to return anything. It's a void. So then I can just print out value again as if it were a variable that never changed. And, you know, this is just a local variable in my main function. And I don't have to do anything to be able to pass it up here and do some math to it. And here it'll output 20. All right, then I print out a bunch of lines. And then I set my pointer, okay, to the address of value. All right, so whatever our address is, let's say it's like 1000 or something. And then I print double data, or sorry, I call the function double data. My value variable with the address operator in front of it, I just pass it a pointer. Now remember, a pointer points to an address, just like using the address operator on a variable gives us the address of that variable. So basically, this is going to do the exact same thing. This and this are the same. They're just two different ways of writing it. You can use the address operator to get the address of a variable, or because int pointer is set to the address of value, okay, right there, well then when we do int pointer here, it's going to pass it in and double 20 to 40 when we print it back out. So let's run this. Get my thing over here and bring it over, and look at that. Very good. 10, 20, bunch of lines, and we didn't have to return anything. Very cool. All right, so that is passing pointers to functions, example 1. Okay, I got a couple more examples. Let me check what time it is, and we might take a little 10-minute break. Yeah. So I'll just pause this recording here. We're going to take a 10-minute break. All right, so we're back from break, and we're going to continue. I've got another example here with swapping a function. So here I'm going to be in week 10, passing pointers to functions, example 2. And I'm just going to close my output window here, and we can see I've got one function called swap right here, and I've got my main. All right. Now, how swap works is there's 3 local variables. So there's an address that's going to be stored in A, an address that's going to be stored in B, and then temp, which is going to be assigned to whatever address A is. All right. What points to the variable temp A. So if A is pointing to an int and it's 100, then we're going to store that value in temp because it's dereferenced, right? We're using that asterisk symbol. So it's dereferenced. So whatever is at the address of A, whatever value is there when we dereference it, will be stored in temp. Then we're going to set the value of A to the value of B, and then we're going to set the value of B to temp again. And you'll see that they'll basically swap around. So it expects 2 input. Here I've got X, which is 100, and Y, which is 200. I'm going to see out on a new line whatever X is, and then I'm going to print out X, which should be 100, and I'm going to print out Y, which would be 200. And then we call our swap function. All right, so that's going to go up here on line 8, and we're passing in the address, right? That's what it wants. It wants the address, and then it's going to dereference that address once we're inside of the function. So it's going to get the address of X, so whatever the address is here, so if it's 1000, and the address of Y, which is 2000, for example, and then we're going to print them back out, and they should be swapped. So let's run it. Hopefully that makes sense. And let's take a look here. Zoom in. So X was 100, Y was 200. Now X is 200 and Y is 100. Okay, we didn't have to even do any return functions or anything. So basically, what's happening here, if I can annotate for a second. All right, is basically here in the swap function, okay, we're going up and we're passing X all the way up into A here. All right. Same thing with Y. We're passing Y up into B. Then we're setting temp to A. So A, or ampersand X when we pass it, A, oops, is 100. Okay. And B is 200 because we've dereferenced these addresses. Now, when we swap them, okay, you know what? Let me just actually, I'm gonna do a better annotation here, and we're gonna do it with my heap and stack example. Okay, so we've got 2 variables, X and Y, okay, and they're on the stack here. So the stack is this one. So we've got X, which is equal to the value of 100, right? And Y, which is equal to the value of 200. All right. Now, when we call the swap function up here and we're passing it pointers, okay, we're creating variables up here in the heap. Okay, so we've got a pointer of A, and it is going to be, address. So the address of 100 or X may be 1000. The address of B may be, 2000. This is where that variable lives. Okay, so those are the pointers. So A is pointing to X here, and B is pointing to Y, right? Because we have X coming all the way up into A, and Y is coming up into B. All right. Then we also have one more variable called temp that we've created. And sorry, this isn't the stack. This is the stack because these variables are created during the lifetime of this function. So we've got temp, which is going to be assigned to the value at the address of A. So A's address is 1000. We know that the address of X, okay, if I put the addresses on the side here, we know that the address of X is 1000. So here we go to A, the address is 1000, so we come down to 1000. The value at 1000 is 100, so temp is going to be 100. Hopefully that makes sense. Okay, so when we call swap, it's a very bad drawing of swap, we're passing in 1000 and 2000, right? We're passing in those addresses from right here, from X and Y, 1000, 2000. All right, so then temp is going to be equal to 100 because it's the value at address 1000. And then what happens is A is now set to B, but it's the dereference. So the value of A is now going to be set to, let me see here. The value of A is now going to be set to the value of B. So B currently, the address is 2000. If we go to the address of 2000 to get the value, it's 100. So this value of A, we go to the address of 1000. 1000, the value is 100. It's actually going to be set now to 200. Okay, so that's what that statement does right there. Then B is equal to temp. Well, we know that the value at the address of B, so B's address is 2000, we come down to the address and we get the value, which is 200. And we're going to set that value to temp, and we know temp is 100. So we take temp down and make it 100. And now, there you go, you got 200 and 100 swapped. All right, and then obviously, after that's done, then all of these are cleared. Oops, I just double clicked everything away. That's how it kind of is working with the swap function here, with me trying to annotate it. All right. Cool. Another example, example 3. Passing pointers to functions, example 3. So here, what we've got is we've got a function called display, and it's going to receive a string of vectors. Now you see I have some consts grayed out because we will do those in a little bit. And I'm not using a prototype because my function shows it before my main, but best practice would obviously be to use prototype. So this is going to receive an address of vectors because here's my address symbol for V. V is my vector that it's receiving for vectors of strings. And V is the local variable that points to the address of the vector, okay? Now the consts are going to stop us from accidentally modifying something since it's a function for displaying text, right? So this first const, okay, is going to basically be preventing us from changing the values of the vector. So the values of what it points to can't be changed. Then the second const here is going to make the pointer constant, so we can't change what it's pointing to, right? So when we have two consts, it's basically making it the values can't change and the value of the pointer or the address that it points to can't change. All right. So let's take a look down in our main here. I've also got an overloaded function. So here's my function display, but now it expects an int with a pointer array that points to an int, and it also expects an int called a sentinel. Now, an overloaded function means it has the same name, but it expects different arguments, and depending what we pass to the function when we call it, it'll call the right function because it knows which type of arguments it's expecting. So we can't set the dereferenced pointer here to a const because we're doing a plus plus. We're using arithmetic on our pointer. Okay, so the plus plus is going to change what that is pointing to in the array, or in the pointer, sorry. So what we could do is we can set the int to a const if we wanted to, and then because it's always going to be pointing to ints, but we won't worry about that for now. So I basically have a while loop here, and while my dereferenced pointer, okay, does not equal my sentinel, and a sentinel is basically just like a key value that you're looking for to end out of a loop. So my sentinel is going to be -1. While I'm pointing to that pointer and it doesn't equal the sentinel, keep printing whatever I'm at in my pointer and then iterate. Okay, this is something that we need pointers for, not references, because we're using arithmetic. So you couldn't do this with a reference. This is why you have to use a pointer. Okay, so let's take a look at the main. So I print out a bunch of strings. I have a vector of stooges, Larry, Moe, and Curly, and they're strings, okay? Then I call the display function and I pass it the address of a vector of strings, okay? So this is the reference, passing it by reference to that vector. Then that's going to come up to this function. It's going to set that vector right here, and it's going to dereference it using the asterisk here, okay? Then what's going to happen is it's going to, if I wanted to, I could use the vector notation. So I could use the dereferenced pointer and get the vector and use the at function and set the vector that we're pointing to a value here to, I could change the string to funny. And then I can also loop through using my for loop here, okay, in this with the auto keyword. So it's going to automatically detect that it's a string, and it's going to do a for each basically. So for each string in my dereferenced string vector, it's going to dereference it and print out the str object in that collection and repeat for each item, right? So it's a ranged based for loop. So it automatically knows. And then down here, this is just an example of something that we won't be able to do when we're setting the vector to point to another address, because I'm going to uncomment these consts. So if I wanted to, when I uncomment this line and I print this out, actually I'll leave it commented for now. Okay, let's run it and we'll see what happens. Okay. So check this out. It printed out Larry, Moe, and Curly. So we know Larry, Moe, and Curly is here, and we pass it up. And basically, we pass it into this v variable, did a for loop, and printed them out. Okay, that's pretty easy. Now, if I uncomment this, and I set v at 0 to funny, well, because it's a pointer, and I'm setting the actual address to funny, well, it actually updates it to funny. Now, let's check out what a const does, okay? So remember, the first const will prevent us from changing the values, so that's this one. Okay. Trying to use my keyboard shortcut, but that won't let me. So the first const will stop us from actually changing the values. So now this will give me a compiler error. If I save it and run it, Oh, look at that. No match for operator equals. Their operand types are const value type. So I can't change this. That's why I have this commented out. Okay, and then obviously if I tried to set my pointer to a null pointer, well, there's going to be no problem with it right now. But if I uncomment this, then it's going to say, hey, you can't tell your pointer to point somewhere else because it's a constant pointer. It's always going to be pointing to this variable. So I'll run it. I'll show you. Look, assignment of read-only parameter v. So right here, v is a read-only parameter, and I'm trying to assign it to point to somewhere else. You're not allowed to do that. So that's why it's helpful to use the constants keywords, because you'll actually get compiler messages that will stop you from accidentally, resetting or erasing your pointer objects. Okay, so we've got this working. Now, let's try the other array. Oops. It's not working when I want to do this. Okay, there we go. So this is going to be an array of scores. So you can see here, it's an array of ints with 100, 98, 97, 79, 85, and then -1, which is my sentinel. -1, basically, we call it a sentinel, is it stops the processing. It's going to be in the overloaded function up here on line 22. And when it hits -1, it's going to exit that loop while the array, dereferenced array, that I'm iterating through with my arithmetic logic ++ does not equal sentinel, and sentinel is a value that I pass to the function. So you can see here, when I call the display function, I'm passing it the scores array that I want to loop through, and then my sentinel value. So I could change this to 98, and it would stop on the second element. Because I'm at -1, it'll stop here. So we'll notice display is the same function name as display up here, but this one expects a vector or an address. So if we do that, that will work there. But if we pass it this, which is an array and an int, then it will actually call this version of display the overloaded function. So here we go. You may have worked with overloading functions in Java before. So here we go. We print 198, 97, 79, 85 in that for loop or that while loop. And then as soon as it hits -1, it exits the loop and ends line. Right? Now, let's say I change my sentinel to 97, right? And I run it. Well, now it should only print 198. And that is exactly what happened because I changed the number that I want this to stop processing at. And that's using arithmetic on a pointer. Okay? We should have one more example here, which is going to be returning a pointer to a function, but I'm going to talk about how to do that first, and then we will actually look at an example in Code Light. So we can, so far we haven't, but we can return a pointer from a function. So we have a function, right, that we pass something into, but then we can also return pointers. So you know how when you declare a function as like void or int and it has to return that type? Well, you can also create a function, here's your function here, and make the type a pointer. And then it has to return a pointer of whatever int, or it has to return a pointer of double, but you have that asterisk there on your function name. And it has to return a pointer to memory that's dynamically allocated in the function. So the data that was passed in, it will return pointers that point to that kind of information. Usually that's what you want to use them for. Okay, so those are the two little key examples where we would want to use returning a pointer from a function. Super, super powerful. Basically, it means that functions can return an address of whatever type we specify in the function declaration. So we can return an address after we finish the function. So how do you return it? Well, this is what it looks like. I'm returning, here's my function name, largest int, and I put the key character of the asterisk on it, and it returns a pointer. That's what that means, pointer of type int. So it's going to return a pointer of type int. It expects two arguments. It expects pointer 1 that points to an int and pointer 2 that points to an int. And if pointer 1, okay, dereferencing pointer 1, is bigger than the value of what's at pointer 2, then we're going to return int pointer 1, but we're returning the address. Notice that's not dereferenced. Okay, else return int pointer 2. And then there's our return statement, and we're returning that address in memory to the bigger number. Okay, you can also return a parameter. So here we have a and b set to 100 in our main function, and we've got our pointer, largest pointer, that points to an int, and we've initialized it to 0. Then we set it to that function that we just looked at on the previous page and pass it two addresses. Okay, so the address of A, which is 100, and the address of B, which is 200. It's going to dereference those addresses and get the values at those addresses. So this could be at address 1000, address 2000. It's going to dereference them and get the values and compare if 100 is bigger than 200, and then return back whatever the largest pointer is. And here, all I have to do, okay, so I call the function and save it into my pointer object, and then I just print out the dereferenced pointer. Because a return statement, it wants to return into a pointer variable. And then we print out that pointer variable dereferenced. Cool? Hopefully that makes sense. And then returning dynamically allocated memory, okay? So here, we take in two parameters. We take in one parameter for size, and then we take in a parameter for what we want our starting value to be. And we're going to create an array of dynamic size and return the address in memory. So this, if you get anything about returning something from a function, let this be the most important aspect of it, okay? Dynamic allocated memory, okay? That's the heap, and we can create an array as big as we want on the heap, and this is how we do it. And the only way we can access that array is through an address in a pointer pointing up to the heap from our stack, right? So remember, before I get into this slide too much, remember at the very beginning of class today, we talked about, that's a very bad. We talked about having all our local variables and everything on our stack. Oops, down here. Okay, this is our stack. And then up here we have our heap. Okay, so up here we can create an array of however many objects. And the only way we can reference it is this connection. This arrow going from our stack, and we have some address that's like hexadecimal code, you know, and that address points up to the heap. If we lose this, then we lose that dynamically allocated memory up here. Okay, so this is a really important concept if you get one thing from today. So here we have a function called createArray, and we are returning an address. Okay, it's going to return a pointer of type int. So we're creating an int array, as you can probably guess. We pass it the size of how big we want the array to be and the initial value. Okay, so now we create a new pointer and initialize it to 0. So int new storage, null pointer. And then new storage equals, we use that keyword new right there. Okay, so what that's doing, okay, if I annotate a little bit, we use that keyword new. We have our heap and our stack in memory here. New int with size, okay? Size is what the user passed in. So if they pass in 5, we're going to create a new array called new underscore storage. I'm not going to spell it all out. 5. And this is the heap, okay? Right up here. This is the heap. This is our stack. All right. So we have a new array up here with 5 elements in it. Awesome. Very cool. Very handy. How do we use it? How do we get it back? How do we get an address that we can reference from our stack? Well, first of all, let's populate the array. So we have a for loop here. And for whatever the size is, okay, setting I to 0, while I is less than size, so we make a variable of type size and initialize it to 0. So basically while I, we set I to 0, while 0 is less than size, which is still 5, so while I is less than 5, iterate through. Then we take our dereferenced array up there plus I. All right, and then equals init value. So if I want my init value, I have a default value of 0, but if I passed in 10, well then this would be 10. Okay, so then my init value would be 10 in this array. And then it's going to plus I, so it's going to go to the next index, so that was at the 0 index. And now recognize that new storage, I know this is probably confusing. New storage is an array, okay? And an array name points to an address in memory. This address up here, let's say, for example, is 1000, okay, on the heap. This new storage is 1000, okay? Now, if we're doing an array of ints, and I know an int on my system is 4 bytes, when I do plus I, okay, I is the size of my int object. It's going to now go to the next element, and it's going to be 1004. And that's going to be where it stores my next value. Okay, and it's going to initialize all my values to whatever my initial value is. So if I want them all to be 10, it's going to make them all 10. All right, and then we return new storage. New storage is our array address. So it's going to return down to the stack whatever that address is. So if it's 1000, it's going to return 1000 right here. Hopefully that makes sense. We'll keep trying. But here we're using pointer offset notation in a loop. We could have used subscript notation if we wanted. It's a little bit maybe nicer for reading. So here, basically we're going to pass in 120, okay, to create this array. We're going to call that function that we just had on the last screen. I am creating an array here on my stack. That's a pointer object that points to type int, and it's going to be allocated by the function. And then because I know this returns an address, it's going to return it into this variable. So I'm going to create an array. I'm going to create 100 elements in that array and initialize them all to 20. Okay? And then I can use it. I can do whatever I want with it. And then I have to delete it using those square brackets and then the array name. Make sure you free up the storage, right? If you don't do this, you're going to have a memory leak. So you have to use that delete keyword because that storage is up on the heap, right? So we have to release it. Okay? Very good. Never return a pointer to a local variable, okay? So I know this is going to be a little bit confusing, but here's a couple of examples of what we don't want to do. All right, so here I have a local variable that I created from inside my function, and I'm returning that function, or I'm returning that local variable from the function. Don't do that because this only exists while this function's running. Okay, so if you're returning the address of a local variable in a function and that variable is on the stack and the function just terminated, now that variable is past its lifetime, and next time the function calls that in the stack, that area is going to have to be reused, and the pointer will now be pointing into that new function activation record, and you're going to overwrite data that is pointing to, and you could trash the stack pointers, the static links, all kinds of really important information on the activation record. So hopefully the program would just crash, or you get an error that you can fix. But if if the program changes data that's not currently being used, then the program may appear to work correctly for a little bit, but then it will break eventually. So these types of errors are really difficult. So never return into a local variable. Okay. So this is a pointer function. It returns a pointer, and we're returning a local variable. Don't do that. Same thing here. This is a pointer function, returns a pointer, and we're returning, into this local variable here. Not good. All right. Okay. And then again, showing you this is different because this one, yeah, we're returning new storage, and new storage was created in here, but you'll recognize that new storage was created on the heap using that new keyword. That's why it's not the same as returning a local variable, because here, we're just initializing it to whatever, and that's not a good practice. Okay, so let's take a look at an example I've got in CodeLite called return pointer. Okay, return pointer. Let's see if I can find it. Passing pointers to function 3. This is the same example that we looked at in the slides. I've got my create array function here. I expect a size and an initial value for those arrays. And I create a new element, okay, using that new keyword on the heap with the size. It's going to be an int array with whatever size I pass to it. And then I loop through, while I is less than my size, iterate, and then new storage plus I equals my init value. So whatever, if I don't specify, then it will just be 0. Okay, then I return the address to that int array from the heap. It's going to return the pointer to location in memory on the heap. And so let's look down in the main function. Here I create a pointer array, initialize it to nothing. I create a size variable and an init variable. I ask the user what they want the size to be. I ask them what they want their init value to be. I call the create array function, pass those two values that the user just put in, and save it into the my array pointer. I print out a bunch of dashes. Then I call this thing called the display function. And the display function, the way it works is it expects a const int const array. So the values that it's pointing to won't change, and the pointing location of the pointer will not change. And it also expects a size. So this means it's a read only, right? It's not going to change any of that. And that's fine. It's a display function. Then I do a for loop while I is less than the size. Just see out the array, okay, for each index. And so it's going to print out the array that I just created from the stack, okay, because I'm passing in my array, which is what I just saved this function into. And then, of course, you have to call the delete my array to free up that memory from the heap. So let's run this program. Let's see what it looks like in the console when we create an array on the heap dynamically. So dynamic memory allocation, that's what's happening right here. So how many integers would you like to create? Well, I want to create 200 integers, okay? What value would I like them to be initialized to? 53. And we print it out, and look at that. There you go. I just got 200 dynamically allocated integers in an array on the heap, okay? And then it just freed up the memory and deleted it. So don't have to worry about that. But very cool. Very, very, very cool. Some potential pitfalls to watch out for, all right? Remember to initialize your pointers. So don't leave them empty because then they'll be pointing somewhere, probably garbage data, and it will maybe mess up something on your machine. Dangling pointers, okay, we talked about that a little bit, where you just leave a pointer hanging and you don't actually do the delete keyword. Not checking if new failed to allocate memory. So sometimes that new keyword fails and it doesn't actually allocate the memory because it's out of space and it can't make something new on the heap. So hopefully you get an error message. Or leaking memory, right? We don't want memory leaks. So just keep an eye out for those things. This is what uninitialized pointers look like, okay? You need to use the initialize syntax and just initialize it to null pointer. We don't want this pointing to garbage data. All right, dangling pointers, okay? Sometimes they're called wild or stray pointers, and they point to data that's no longer valid. So they might point to a function with a local variable on the stack. Here, a pointer that's pointing to released memory. So say I had a pointer and then I deleted the allocated memory, but I had two pointers and they pointed to the same place, and one of those pointers released the data already, and I discarded it using that delete keyword, but the other pointer is still trying to access it. The other pointer is still there. And so, it's going to point to memory that's invalid. So we would see this also if we're pointing to a function that returns a local variable, because that local variable is past its lifetime. That function's over. That local variable doesn't exist anymore. If we're pointing to it, we're going to get a dangling pointer. Not checking if new failed. So if we try to dereference a pointer that's null, our program will crash. So if new fails, an exception will be thrown. We can use exception handling to using exception handling. Dereferencing a null pointer will also cause your program to crash because there's no value at that pointer object, right? It's null. Leaking memory, obviously forgetting to release that allocated memory with the delete keyword. If you lose your pointer to the storage that you allocated on the heap, you'll have no way to get it back, okay? So that memory is orphaned or leaked, and it's one of the most common problems with pointers. So when you allocate that storage dynamically, the storage has no name associated with it, okay? So if we make an array on the heap, it's just an area of memory that's just returned to us and stored in the value of a pointer, right? So if I make an array, This is the bottom line of what I'm trying to get home today. If I make an array, and this is the heap up here, okay? And this is my stack. Okay, if I make an array called ARR on the heap, it's just simply an area of memory, and it's returned to me on the stack via the pointer. Okay. Now, if I lose my pointer, okay, if I lose that, then I lose the allocated memory from that function, right? So if I get my eraser here, I lose that reference because I don't have that pointer anymore. And if the pointer was declared in the function and the function terminates, well, then you just lost your pointer as well. There's no way you can reference the allocated memory up here on the heap. This memory is still considered in use by C++, okay? Where we lost that connection. So this is called a memory leak. And if you leak enough memory, you could run out of storage on the heap for future allocations. Okay? So that's a memory leak. Smart pointers versus raw pointers, we'll talk about a little bit in the future if we have time. These are raw C++ pointers. C++ has smart pointers that take care of a lot of the problems that we were talking about. They're very efficient, but it's a way more advanced topic, and it's something that we should learn as we become more proficient with C++, but as this is an intro to C++ course, we'll revisit those in the future. If you ever want to look into that on something on your own, then I would suggest that as well. Also, in object-oriented programming, we might talk about smart pointers. So conclusion, when do we want to use pointers versus reference parameters? Well, pass by value, okay? Think about this. Pass by value is the default in C++. When a function doesn't modify the actual parameter, okay, and the parameter is small and efficient to copy, like simple types, like int, char, double, then we just use pass by value, right? Strings and vectors have overhead when they're copied, and so those are bigger data types, so that's when you start thinking of using a different way to pass it to a function. So pass by reference is what it's called when we use a pointer. And a lot of data structures rely on pointers, being null at the end of the tree. Pointers can be null, references can't be null. So when a function has to modify the actual parameter and the parameter is expensive to copy, so like a big vector or a big array, and it's okay that the pointer is allowed to have a null pointer value, then we'd want to use a pointer. All right, now if the function does not modify the actual parameter and the parameter is expensive to copy, it's also okay to the pointer to be a null pointer value. Then this is maybe suitable when we want to display a vector, okay? So we don't have to modify it, but now we use that const keyword, okay? So it's okay that it's null. It's okay that it's an expensive copy, so because we don't want to copy it, we use a pointer just to modify the original, but we also don't want to modify it, so we just use the const keyword. Okay, so this would be suitable when we're displaying vectors. When we pass by reference using a const pointer to const, this is suitable when the function does not modify the actual parameter. The parameter is expensive to copy, like a vector. It's okay that it's null, and you don't want to modify the pointer itself, like the address it's pointing to. So the pointer's not moving, the data it's pointing to isn't going to change. That's when this is a suitable option. Hold on with me, 2 more slides. This option, pass by reference using a reference, okay, so if you remember way back to the first slide in this PowerPoint, we used that reference symbol, the ampersand. When the function does modify the actual parameter, and the parameter is an expensive copy, and the parameter will never be null, then we can use a reference parameter, okay? And we use pass by reference using a const reference, okay, so const with the ampersand, when the function does not modify the actual parameter. So if it's a display function or a print out to the user, but it's still an expensive copy and it can't be null, then we would use a pass by reference using the reference parameter with the const keyword right there. Okay, so maybe a display statement. All right, so in conclusion, Pointers and references are very powerful. There's great responsibility that comes with them. You need to make sure you initialize them so that there's no garbage data. You need to make sure that you delete them so there's no leaks in your memory. C++ programmers, being in control of their memory and their hardware is something that I referenced at the very beginning of this course, and how C++ is such a powerful language that we have access to things on our machines and aspects of our application memory that many programmers don't have access or control over, which is really, really cool. It's scary, but once you learn it and get a little bit of experience using some of that stuff, it's really, really satisfying to be able to do that kind of stuff. It's different than any other language, honestly, Java, Ruby, etc. Not to knock on those languages, but just really cool that C++ allows you to have that option. So hopefully, this was definitely a big section. This was a confusing section. If there's things you need to go over, ask me questions, send me emails, watch the videos over again. I really would love you guys to understand this and to get this, especially with the assignment that we'll talk about in a little bit. But super cool stuff. Hopefully it was interesting for you guys, and that a couple of those main points stuck. So I'll end this recording here, and then we'll get into talking about the assignment.